Welcome to Chapter 12. This chapter focuses on cryptography attacks as well as defense. What we're learning for this chapter is we're going to be learning about the different types of cryptography, what it is. We're going to be looking at the different types of keys for encryption, symmetric and asymmetrical. We're going to be looking at popular encryption algorithms. We're going to be looking at things like MD5 and SHA and discussing the differences between these types of hashes. We're going to be looking at digital certificates and signatures and how they kind of play in stenography. And we're going to be looking at knowing different encryption cracking tools. That's kind of important when we start talking about cracking Wi-Fi. So the function of cryptography, the process to conceal the contents of a message from everyone except people that know a unlocking key. That's encryption. Encryption is converting plain text to some type of ciphered text. Authentication normally can be done through something that you know versus something that you are, something that can verify that you are who you say you are, and that you have the appropriate authorization to view that content. Integrity, that it stays unchanged, confidentiality, that it's still private, and non-reputational. Basically ensure that the sender of the data receives proof of delivery. Okay, so the big thing here is understanding that I may want to send you a message, but I want no one else to read that message. We can set up a encryption sequence using a specialized algorithm. Basically, I will encrypt a message with one of my keys, and I will email it to you. Well, because I've already mailed you my physical or my unlocking key, you'll be able to take the unlocking key and decrypt my message. Now, the big thing here is symmetrical, both keys unlock and lock it, or encrypt it and decrypt it, versus asymmetrical, and that is where one will encrypt and one will decrypt. All right, some of the history is it's throughout the ages, it's used by a lot of the ancient societies like Sparta, Hebrews, ancient Rome, Julius Caesar, Antisus Caesar cipher. That was just a very simple substitution cipher. It's used in crypto systems such as plain text, ciphertexts. You guys can go through the list, but the big thing here is, again, it's making sure that you can send and receive messages while only allowing those with the appropriate key to decrypt your message. Different algorithms that are used, and that's going to be the set of rules that will be used to encrypt and decrypt the data. The algorithm is how, or the rule structure, to both encrypt and decrypt. So plain text will be encrypted with a different key on a different algorithm, produces different ciphertexts. Meaning if we're using one type of algorithm, the actual ciphertext may be different based off of the algorithm that is being used. Again, symmetrical keys use the same key for both. Asymmetrical use different keys for one for encryption, one for decryption. Common symmetrical encryption could be things like DES, Blowfish, and Renja, RC4 and 5, and Safer. So, this is an older of the two forms of encryption. The main advantage here is it's easier. The main disadvantage is key distribution. And this doesn't really provide a whole lot for authentication because anyone that has access to your one key can then decrypt it. So that's kind of bad. It's fast and hard to break if a larger key is used. It's very common. That's why we end up with larger and larger key sets. So let's go and look at DES. DES was developed by the National Bureau of Standards, now called NIST. It uses a 56-bit key, and it must be recertified every 5 years. By early 90s, it was outlived its usefulness, so we started looking for a new way to replace it. And in 1998, the Electronic Frontier Foundation cracked it in about 23 hours. Now, it's not even hours. So, this functioned as a block cipher. The segments the input data into blocks, processes each 64-bit block of plain text at a time, and it'll give you a 64-bit ciphertext. Again, it's going to be based off of that 56-bit key, and it performs 16 rounds on every 64-bit blocks. The big thing here is it has 4 modes or types. The ECB, or the electronic code mode, the cipher block changing mode, the cipher feedback mode, outback feedback mode. Triple des was implemented to extend the usefulness of single des. Basically, it uses 3 of the 56-bit keys, making it 168-bit. Again, it's still fairly old and it's not as common anymore. Alright, so because that was outdated, we have 2 new developed ones. We have the Advanced Encryption Standard, AES, and the RC, or Vivid cipher. So in 2002, NIST replaced DES with the Renadil cipher. And so this iterates the block cipher supporting variable keys and block lengths of 128, 192, 256, and so forth. It's considered faster and simpler to use than the 4-step parallel series of rounds. Most of this you can read yourself. The big thing here is RC basically took over the DES standards, and we're currently on RC6, which is a variable key size and variable rounds, making it simpler and faster depending on what we're trying to encrypt. AES requires 2 keys, a public and private. The public key is given to anyone, the private key is kept secret. Uses difficult mathematical problems to help apply to it. The RSA, which was developed by MIT and someone at MIT, not developed at MIT in 1977. It uses 2 large prime numbers and works on the principle of factoring them. It's used for encryption. It's used by both Internet Explorer, Firefox, as several other web browsers. We have the Diffie-Hellman version, we have the L-Gamble version, and we have the ECC version. The ECC was used for many things like smaller handheld devices that are less powerful. The L-Gamble one was used for encrypting digital signatures, while the Diffie-Hellman was used for IPsec. But it's vulnerable to the man in the middle type attack. Man in the middle, not main in the middle. So let's talk about hashing. Hashing takes the variable amount of data and uses an algorithm to produce a fixed length hash value. For example, your password. It'll run an algorithm against your password, and it will hash it to something that's unreadable, at least to us. But the algorithm can always reverse it, so it can go from your password to the hashed value if you run the algorithm. Again, through the hashed value or the reversing of it, the hash value should be able to then contemplate your password. It's used to provide integrity, verifying that nothing was changed in transit. Collision, it's when 2 or more different files produce the same hashed value. That sometimes does occur. We have 2 main types of hashing. We have MD5, which produces a 128-bit hash value, and we have SHA-1, which produces a 160-bit message digest hash. So the big question here is they look similar, but how are they different? Their diagrams include chunks of bits and bit rotations, XORs, and special features. So the big thing here is which one is better. One article actually says SHA-1 is better because the MD5 actually has more collisions. Other articles will say SHA-1 is actually worse because the operations of it actually provide collisions 2 to the power of 61 times rather than the MD5 version, which is 2 to the power of 80. So again, everyone has different opinions on which is better and why, so you must keep that in mind. So the digital signatures, basically the application of asymmetrical encryption for authentication. It's similar to a real signature, but it uses 5 basic steps. It's used to validate the integrity of a document and identify the sender. If you want to go and sign a document, like for example, a PDF, I will sign it with a digital signature that I have created that actually verifies my credentials, my login, my computer name. That way, that combined actually shows that I am who I say I am. Steganography is actually the mechanism used to hide information in plain sight. For example, hiding data in a photo. That's steganography. The actual amount of information hidden depends on the size of the carrier file. We can take a normal like 4 meg photo and we can pump it full of information and we can turn it into like an 8 gig file. That's kind of large, but I mean, you can pump a lot of information into a photo, but the more information you pump into it, the larger they become and the more that they start sticking out. Steganography tools could be things like snow, and that's one tool for hiding messages in a document. If you're using stag hide, that will hide messages in sound files, image hide, or S-tool to hide things in photos. Remember, Steganography helps to discover and extract steganography content. That way, if you think you actually have a file that has hidden content, you can use the snag analysis to actually see if you can extract usable data out of it. Digital watermarks is another one. This is more of a commercial application of steganography. Acts as a type of digital fingerprint. That way you can see who legitimately owns the work and verifies that they own the work. It's normally used in IP theft, intellectual property theft, to show proof of ownership. Adobe Photoshop does include this, though it's not always the easiest or funnest to play with. Digital certificates. Normally, if you want to go to a website, how do you know if that website is trustworthy or not? Normally, like you go to Google, it will be HTTPS. That means there's a certificate there. But who issues that certificate? Who says that that's really Google? We have a certificate authority, like VeriSign. VeriSign is one of the big ones. So, for example, I'm going to use Microsoft Edge, and I went to Google. It redirected me to the secured portion, so I have a lock. So here, the certificate authority is called GeoTrust Global, and they have identified the site as google.com. They trust the site, and we trust GeoTrust Global, so thus we trust Google because we trust them. That way we can have a mechanism in place to trust websites when we need to. How do we distribute keys? And how do we distribute certificates? We normally have a public key infrastructure, or PKI, and they are the ones that actually are the certificate authorities. They actually have a process for registration. That way we can request certificates. They have servers that will issue certificates, but they also have this important item, a certificate revocation list, CRL. That way, if they revoke a certificate, it goes on the list, and these lists are checked quite often. So different trust models could be a single trust. That means we normally don't use a third party, or if we do, we're using just a single third party versus a hierarchy trust, where that's actually where we trust a top layer root certificate or root certificate authority, and then they may issue certificates to their underlings, and the underlings may issue certificates to their underlings, and eventually we get our appropriate certificate. The web of trust, we've already kind of talked about. That consists of many supporters that sign each other's certificates. And because we trust the web of trust, we trust the certificates that they're signing. That's less common, but it still exists. Things that could use our certificates, things like SSH, SSL, PGP, Secure MIME, IPsec, PPTP protocol, our EFS. So lots of things that use certificates. Even though we're not always aware of them, there are lots of devices out there that use certificates. So one of the last things we have to talk about is talking about encryption cracking. There are several types of cryptographic attacks. There's known plaintext attacks, ciphertext attacks, man-in-the-middle attacks, replay. You can go through the rest of them. The big thing here is understanding that encryption is not 100%. The newer forms of encryption make it harder, but not impossible to decipher or decrypt the data. The weak encryption could be things that use XOR, base64, or Unicode. These are all older encryption technologies that have been shown to, well, be very weak, to be able to bypass encryption very fast. One of the last things we have to talk about is the actual encryption cracking tools. Things like John the Ripper, that's a very big one. Crack or Evercrack or path cracking. Each type of encryption cracking tool is going to be for specific items. John the Ripper has been one of the primary tools that I've used for cracking encryption, but each of the different types of encryption cracking tools are going to vary pretty much month to month, week to week, because these tools are always being redeveloped, reanalyzed, made better, or new tools are coming out. So keep that in mind. That's actually for this chapter. I want to thank you, and hope you have a great day.